Welcome back. We have been discussing on helium ion microscope, particularly for imaging, surface imaging, knowing that means finding the surface topology. And in our last lecture, we also have seen how helium ion microscopy along with SIMS can be used for measuring the composition or elemental composition, and chemical analysis can be done with a helium ion microscope attached with a SIMS. Today in as a last lecture on helium ion microscope, I will discuss what additional things that you can do in a helium ion microscope, whether you can create features of nanosize, or you can deposit features of nanosize using a helium ion microscope. So, that is what we will see, how these ions can be used to mill the surface of the specimen and create the structures of the desired size, and for that what parameters need to be controlled, and also how one can deposit certain materials on the specimen to a desired size and shape. So, modification of the materials using helium ion microscope is not new, because we know until helium ion microscope come to prominence, we have scanning electron microscope. Several decades before, scanning electron microscope have been also been attached with ions for this lithography purpose or ion milling purpose. Particularly gallium ions have been used for several years now to create features to a size in the micron or submicron levels. So, in that respect, helium ion microscope also capable of doing it with a much finer size, as you will see here in today's lecture. So, we can certainly modify the materials using an ion beam through milling or through deposition. So, first is that because a focused ion beam is placed on the specimen, that is why we say it is a focused ion beam, FIB, and it can produce nanostructure of desired shape and size. One can also do the selective deposition of noble gases ions using the noble gases ion. If suitable precursor are available, we can do the etching using the reactive ions, and we can do the patterning and also other such application using ion microscope. So, in our ion microscope, ions are bombarded on the specimen, a fine beam of ions bombard on the specimen solid surface, and that lead to many different processes. We have seen in our last lecture that would sputtering can be occurs, sputter of target atoms can be done, and by sputtering the atoms from the surface, we can create a pattern on the specimen, resulting in direct patterning of the sample can be done. It can also generate excited surface atoms, which have no enough energy to be sputtered out, but still they can influence in certain to fulfill certain objective. Because ion beam is striking on the specimen, it can do the local heating, and that thermally dissociate and lead to local chemical vapor deposition of the specimen, that can be done. It can certainly damage the target material and also implant the incident ion that we would like to implant, and it can also help in producing electromagnetic radiation that is nothing but ion illuminations. All these things can happen in a ion solid interaction. If we look at we have been previously discussing on the interaction volume. So, in that interaction volume is nothing but we have been discussing for electrons and ions as like a teardrop shape. This is our interaction volume. We have been discussing only one thing, and from this region the signals that comes, that is secondary electrons, has been used for imaging purpose. But now first time we are coming with a primary and secondary sputter volume. Sputtering will occur certainly at where first it is ion or electron beam is incidenting. sputtering will be less with electrons certainly, but with ions because it is little heavier mass, sputtering will occur. More heavier the ions, more sputtering will occur. And the region from where it first bombard on the specimen, this is the primary sputter volume, and this is what the primary sputter volume. Almost like if we look at the different ions, compare with different ion, helium, neon, argon, xenon, then xenon or also krypton is there. So, all these different ions, what we can see that for helium, this is one, this is primary volume, primary sputter volume, and this is secondary sputter volume. This primary sputter volume is smallest area of around like it is around like maximum 5 nanometer, and the secondary if we combine the primary sputter volume and secondary sputter volume, then it goes to quite large for this black color helium ion microscope one. But if we go to heavier mass more than argon, let us say more than argon is a green color one, it is almost like green, almost above the argon we have almost like one interaction volume. There is no primary and secondary, it cannot be different, the primary and secondary interaction volume cannot be differentiated. So, what happens exactly? As we know, once there is let us say primary incident beam is primary ion is incidenting on this specimen. So, from near the surface, this is around 5 nanometer, let us say 5 nanometer, that is around 5 nanometer. That is the primary interaction volume. We can say primary interaction volume. From those places we get secondary electron 1, and I will write here ISC because here it is ion induced, and from that region also we have backscattered ion BSI, we have also backscattered ion, and we can also sputter away some of the atom, we can also have sputter atom, all this can happen from there, from the region where that strikes the beam. So, now that ions can go inside, and some helium can be incorporated into the lattice in the specimen, and it can go as deep as like as deep as 300 nanometer, it can go down, and while it comes out, this can come out here also. So, this can be after its changing its trajectory, some of the things sputtered target ion. So, when it comes out from this region, you know our secondary electron 2 comes out, and the yield of the secondary electron 2 with a helium ion microscope we know very low compared to the scanning electron microscopy cases. When in case of scanning electron microscopy cases, we say it is a backscattered electrons. When backscattered electrons comes out of the specimen, they also produce secondary electrons that we name as Sc2. So, here also we name it is Sc2, or you can write ISc2, Sc2. So, now in this region also we can have sputtered atoms, sputtered target atoms, all this can happen, and this happens in a depth of few nanometer from the surface. And now this region is our secondary sputter volume, this is the secondary sputter volume, which is much larger, relatively larger, are around 300 to 500 nanometer compared to the primary interaction volume, primary sputter volume, which is very small. So, then this will occur for the helium, but as you see for the argon above argon atoms which are heavier, we see only one region, that is because their mass is higher, their momentum will be higher, producing a little, certainly here you can see the difference, helium giving a very helium giving a very small spot size here. Unlike the cases as you see, as you increase the mass of the ions, they cannot, beam range become less, they cannot penetrate much deeper into the specimen, and also that lateral direction also increases as you go to higher mass, the lateral direction also keep on increasing. So, in these cases like above argon, we have only one type of interaction volume. On the other hand, here as these are going, these are secondary interaction volume or secondary sputter volume. So, this sputtering, what influence this type of sputtering or milling? So, first thing is the material properties, mass of the target atom and its elemental composition. So, the as per the elemental composition and mass, the interaction volume will also change. It also depends on the density, all these things will change. Similarly, if the composition it may have a composition where some of the atoms can be easily spotted away, while other spotted atoms, other atoms may not be easily spotted away. If that happens, then what will happen? There will be non-stoichiometry in the specimen. The atoms which are easily spotted away can go away, creating a non-stoichiometry. So, these are the effect of mass of the target atom and its elemental composition. Crystallinity and crystal orientation. Like if the crystal orientation aligned with the ion beam, then more channeling occurs, we have seen. So, because of channeling, ion beam will penetrate much deeper into the specimen, and therefore, less number of less chance of sputtering to occur. So, that is effect of the crystallinity. So, crystallinity and crystal orientation when changes, the sputtering will also change and milling effect will also vary. Third thing is surface morphology. Surface morphology is nothing but the creation of 3D features. When incident beam strikes to the specimen at a normal incidence and at an angle normal to the specimen, then the sputtering amount of the atoms will not be same when the angle is different. So, as the surface morphology changes, where the tilt angle automatically changes on the specimen, thus milling performance will also change. Fourth thing is electrical conductivity. So far most of the studies have been done with a conducting sample or metallic sample, because anyway helium ion microscopy is quite new in the history. It is not more than approximately 15 years now. As most study done with metallic sample, it has been found that electrically conductive sample is good. On the other hand, if the sample is not electrically conducting, what will happen? There can be some charge development or local charge development or potential development at the surface, and that can affect the trajectory of the sputtered atoms or incident ions. So, electrical conductivity also plays a role for milling. About the incident ions, certainly mass of the ions is more sputtering will occur or more milling will occur easily. Energy of the ions, certainly energy of the ions, as the energy of the ion increases, the sputtering yield increases, sputtering rate increases. Angle of incident is nothing but the same thing, surface morphology. The angle between the incident ions and the sample surface tilt angle also will influence the milling of this specimen. Here you see an example of nanostructuring of the gold film using a helium ion microscope. Here this is a gold film of thickness 50 nanometer, and it is milled of size around 25 nanometer to 25 nanometer region was milled, producing a chessboard type of pattern, creating a features like square type of feature, pillar type of features of the gold film. And in the right side what you see, there are trenches are drawn of different depth. These are more depth than the left side one, by changing the dodge, the ion dodge on the specimen with a 10 nanometer period. So, what we have seen here, these are of size approximately 5 nanometer, which is very small if we compare the patterning of the structure. So far none of the techniques available which can produce such small features by milling, as that what you see here with a helium ion microscope. The different trench depth can be changed, as you see in the left side. The depth is less 0.5 nanometer to 10 nanometer. So, which illustrates the possibility of creating 3D structure with direct focused ion beam sputtering. So, it is done by varying the exposure dose. By varying the exposure dose, we could create 3D features, 3D structure of very finer size up to less than 5 nanometer, which no other techniques provides at present. Here is another example of sputtering yield of the helium ions. As the dose, the incident dose of helium ion changes, the sputtering yield will change. In the left side, you see a helium ion microscopy image, where a dots or a pores are created by milling with different dose of the helium ions. In the when we go to in downward direction, the dose numbers are increases from twice, and in the horizontal direction also it increases like 1, 2, 3, 4, 5. In this manner, it can be increased. And what we see here, and this is the AFM image, atomic force microscopy image, and that providing the portion where it is a red circle, and in the right side you see how the dose effect on the milling depth. Milling depth was measured by atomic force microscope. As we see, as we increase the dose, milling depth increases and then becomes saturated after a certain dose. So, in another important features you can see here, for example, when dose is increases, you see in the, around the pores there is a brighter region. Brighter region means more number of secondary electrons are emerging from the region. That is due to the swelling. Swelling occurs around the milling area. Swelling occurs around the milling area when the dose helium ion dose increases above a certain threshold value or optimum value, which we can see above 16, we could able to see such kind of swelling. And swelling occurs why? Because as helium ion penetrates into the specimen, some will go and stay in the interstitial, some will outgas. But when they will accumulate at the surface, they will create a stress, and due to this stress, that material will start to swell. If the outgoing is not enough, outgoing gas is not enough, slowly they will swell and then they will crack, and the crack you can see here when the dose become very high. So that will happen when you cross above certain ion dose, that you can see the swelling and cracking will occur when the dose increases above an optimum level. So, another example that is one of the drawbacks, that means when you have a much higher dose. Second drawbacks or disadvantages is that long range order sputtering of helium ions can be observed experimentally when large doses are involved. Long range order sputtering means sputtering occurs much away from the specimen also. As you see, some of the black portion here, the dark area, darker region around the mill box indicate removed gold, and their size is around 300 nanometer. This is known by AFM thickness measurement. As you see here, in this region, the thickness or depth is around 2 nanometer depth. This region 2 nanometer depth. This is a 2 nanometer, and this area from here to here is around 300 nanometer. It is almost more than 300 nanometer. This area, and we have a depth, that means the pore depth is approximately 13 nanometer. AFM profile showing indicating that though we want to mill only this small area, but some of the unwanted materials are also removed around the area of interest. This is what the secondary interaction volume or secondary sputter volume. So, when the helium ions go here out, it also will take out some of the gold atoms region around the specimen. This is what the secondary sputter volume, and in this way this is one of the drawbacks, though we do not want to mill this area, but automatically it will be done because of this. You see here an example, another example, creating the gold plasmonic antenna. That the top one is the gold nanorods created by electron beam lithography EBL, and then these are the area from where the milling is done by helium ion microscope, creating a features or gap of size as small as 3.5 nanometer, and this is only possible at present with helium ion microscope, no other techniques. And another example here, what you see the application of helium focused ion beam creating the coaxial plasmoning gold nanostructure, creating here in the left side one, it is a gallium focused ion beam, creating a 30 nanometer gap. Actually, the interest to create 30 nanometer gap, but it produced quite a larger gap with a gallium ion as compared to when we do with a helium focused ion beam, it produces exact 30 nanometer gap of this coaxial nanostructure with a and this region, edge region are quite sharp in case of helium focused ion beam compared to the gallium focused ion beam. Gallium focused ion beam is extensively used along with electron microscope, scanning electron microscope for creating such kind of features, but as you see here the creation of the structure nanostructure is much more efficient or precise in with the helium focused ion beam, and here you see one can create 8 nanometer gap with a you can do the milling of very small size using helium ions. So, advantage of helium ion focused ion beam is the main advantage of using helium focused ion beam in the fabrication of nanostructure of very small size with a high reproducibility and reliability, within the range of 1 nanometer as compared to any other fabrication technique. We have seen that any size shape can be designed with helium ion microscope with an example of gold is being presented here. Now at present we have only helium ion microscopy that is capable enough to do such nano engineering of size below 5 nanometer. Another advantage of helium focused ion beam is that magnetic materials can be done. When we do with electron microscope or scanning electron microscope, we also see the features by bombarding the electrons at the same time, but if the sample is magnetic in nature, then beam distortion occurs, electron beam distortion occurs because of the magnetic field of the magnetic sample, but the magnetic field of the sample will affect less to the ions, incident ions. Therefore, magnetic materials can be easily done, the nanostructuring of magnetic materials can easily be done with helium ion as compared to the that done with helium ion in helium ion microscopy as compared to the ions in electron microscopy. Then second things is what we can do with again helium ion microscopy is the gas assisted deposition with noble gas ions. We can do deposition of the materials using these gases, using these ions. So, we can simultaneously introduce volatile compounds such as organometallic compounds, halides, halogenides in small quantities into the chamber, and then we can deposit those on the specimen surface. As you see here, we are injecting the precursor material such as organometallic compound, and our incident ion is coming, and then these precursor material will adsorb on the surface, physi-adsorb on the surface, and when incident ions strike, then what will happen? Then they will interact with the organic materials and they will dissociate and degrade, and during the process deposition will occur on the specimen where incident ions interact with the specimen and also the precursor material and producing a deposition in the region of interest where ion beam is striking. Other things like volatile fragments etc. will go away. So, accordingly one can create 3D structures by selectively depositing the region of interest and locally doing the dissociation and decomposition in the specimen inside the microscope chamber. It can also enhance the physical milling rate by adding compounds which locally decompose upon ion induced dissociation. It can also do like we can increase the milling rate also by allowing such some reactive gases that we have seen before, like sesmium, oxygen radicals. We can also pass them, and in presence of ion beams we can also do the milling or etching, that can also be done. Dissociation and deposition. First, that organometallic compounds which are coming as a precursor, they will adsorb on the specimen and they will be dissociated and deposition will occur. So, that effects dissociation reaction depends on the energy of the primary ions, and generated excited surface atom. Some of the surface atoms will be some of the atoms will be generated which do not have enough energy to come out of the specimen. So, they will also participate in the reaction, and also ejecting secondary electrons, they will also participate in the reaction for the dissociation, and also some temperature arises in the process. Deposition can be either reaction limited or mass transfer limited. It is reaction limited when we have we will say reaction limited when there is more adsorbates than dissociation, more adsorbates are available than dissociation. When it occurs, when enough number of adsorbates molecules are available or adsorbates are available, then dissociation, that process will be called reaction limited. When it is opposite, when more dissociation is occurring and less adsorbates is available, then it will be mass transport limited. Process of deposition. The number of available adsorbates in the irradiated region depends on the 4 contribution, like injected molecular flux, like the precursor onto the substrate and the reaction zone, and the desorption rate depending upon the resident time, how long it will stay of the adsorbates, surface diffusion rates, how efficiently they can diffuse in the surface on the surface, and depending upon the adsorbate mobility on the surface, and dissociation rate of the adsorbates depending upon the dissociation rate. All these factors will determines the reaction process here. And the factors that influence the deposition and its rates are like first is pixel dwell time. Pixel dwell time is normally in the nanosecond to microsecond. How long our ion beam stay at one spot, that is the pixel dwell time. It is nanosecond to microsecond. If it stay longer, then what will happen? Deposition rate will be decreasing, because when it stay longer after a certain time, what will do it, rather than depositing, it will do etching, it will removing the specimen or sputtering away the specimen. So, it will decrease the deposition rate when the dwell time is more. Pixel refresh time, when pixel means ion beam falls, then it gives some interval, another ion beam falls, that is the refresh time. Now, during the refresh time, the precursor get refilled. So, if refresh time is more, then it will increase the deposition rate. And then become saturated. So, it is the refresh time versus deposition rate or growth rate. It will increase, then it will be saturated, and normally it gets saturated at around the range of 5 millisecond. After 5 millisecond, it gets saturated. 5 millisecond, saturation occurs. Then pixel distance or overlap, distance between 2 pixel. If there are more, then again it increases the deposition rate, then becomes saturates. Pixel distance increases means it will be increase and then it will saturate.
These are the different factors that influence the deposition and its rate. One can create 3D structures as you see here. This is done by taking a precursor called trimethyl methyl cyclopentadienyl platinum. A precursor is introduced into specimen, then ion beam falls. Ion beam of different current, as you see, is taken, different current 1.5 picoampere, 2 picoampere. As you see here, upon increase at a lower current, beam current or probe current, we can have a much sharper tip and much narrow nano rods. This is a tilted view of the pillars, that will produce a much taller pillars with a narrow width. By upon increasing the current or dodge, we could see that it is the volume of the materials deposited also less, because at a higher current enough precursor will not be available. Whatever the current available, quickly precursor is getting dissociated and deposited. Enough precursor cannot come quickly, and then when enough precursor is not available, then it will start milling, enriching. Therefore, the volume here decreases when you take higher current. Moreover, other features, that means another things happen, that higher current, beam current, it is a wider diameter pillars, that indicates that is a vertical growth, that means that is also a sideway growth here. So, these are theoretical simulated cross section of the pillar. So, at the center there is a effect of the deposition is due to deposited by primary ions and SE1 at the center, and near the center. This yellow color is due to SE1 and the red color is due to the primary ions, and the lateral growth this side is due to scattered ions, the green color, and finally due to SE2, the cyan color, this color. So, this SE2 is playing the role for lateral growth SE2. On the other hand, primary ions is the middle portion growth, and at one place you keep on you allow the ion beam to stay at one place, and you keep on growing vertically the structure. From this precursor we could grow platinum PTC, platinum carbon on a silicon surface. Similarly, many other type of structures can be produced by helium ion microscopy purpose, using the helium ion microscope. One can do also patterning, local modification of the material using ion beam, and surface patterning can be done. In these cases, as you see, it is a sodium chloride crystal. On the sodium chloride crystals, first ion beam was made to scan in a manner of like this, of a particular size. After it gets scanned, that is what the local modification is done. Then you see that is a ion luminescence image, Once the ion beam scan of this area of sodium chloride crystal, this region get modified, or nothing but more number of defects is created because of ion beam interaction. As the defects is created in this region, they produce luminescence, which we do not see here. This is a complete flat surface. Here this is a secondary electron image. You see there is no change in the darkness contrast, the brightness contrast. So, it is uniform, there is no changes, but here you see the clear difference of the ionoluminescence, because though this is flat, these regions have a different defects concentration compared to other regions, therefore, giving a different contrast. This is what nothing but surface patterning or local modification of the surface using helium ion. So, in conclusion, what we have seen here, that helium ion can be used for fabrication or creation of the structure by milling or deposition of size smaller than 5 nanometer, and we can produce the structures using suitable precursor material such as organometallic precursor, and for the creation of the structure different parameters can be varied judiciously, so that you can able to create the shape and size you desire. A higher dose would lead to formation of the secondary interaction volume or spotter volume, and also can create also surface damage. Those has to be taken care while doing this fabrication using the helium ion microscope. These are the references. Thank you.